Hello everyone, my name is Ayşen Derli. I'm a doctoral student at Tampere University under the supervision of Professor Serkan Kranyas and Professor Monsef Kabuş. Dr. Mohammed Chowdhury is our collaborator from Qatar University. In this video, I will present you OSegNet Operational Segmentation Network for COVID-19 detection using chest X-ray images. Coronavirus disease 2019 is caused by SARS coronavirus 2, which affects seriously people in high-risk groups and especially the elderly. The disease can lead to intubation, hospitalization, and even death. The disease is highly infectious, which brings many challenges to the healthcare systems, especially its mutations are even more contagious, making it harder to track and locate. Therefore, accurate and fast detection of COVID-19 has the utmost importance to prevent the spread of the disease. However, the diagnosis is challenging due to its similar symptoms with other viral infections. There are several diagnostic tools to detect COVID-19. One of them is nucleic acid detection with real-time polymerase chain reaction, which is also known as PCR test. There is also computed tomography to monitor the patient's lungs, and also chest X-ray imaging. The PCR test has high false alarm rate and is slow. On the other hand, CT imaging is expensive and it causes more radiation exposure compared to chest X-ray imaging. However, chest X-ray imaging is fast and it has the easiest accessibility. Therefore, in this study, we used chest X-ray images to detect COVID-19 from. In the literature, many studies have used deep learning models for detecting COVID-19 from chest X-rays, especially by transfer learning. However, these studies have several limitations. One of them is data scarcity. As we all know that deep learning models need a lot of data to generalize the problem from. However, when there is limited data in the training set, there is an overfitting issue. Also, previous studies have used control group that is formed by health subjects only or limited pneumonia types. This can cause a problem in real-life case scenarios, especially in hospitals. And there is a reliability issue for deep learning models. When we check their decisions, we have seen that the decisions are coming from irrelevant areas on the images, for example, from background or text areas. However, we expect them to come from the lung areas only. And also, convolutional neural networks are very popular that have convolutional layers. However, these networks has homogeneous network structures since they have linear neuron model. On the other hand, operational layers have nonlinear neuron models. That's why they can have a superior learning performance compared to convolutional layers, and they have significantly reduced the network depth and complexity. So in our study, we have overcome the limitations of the previous studies by proposing the largest COVID-19 dataset that is called CATACO-19. So CATACO-19 has the largest COVID-19 chest X-rays that has the segmentation mask, and also its control group is formed by healthy subjects and 14 different lung diseases. In this study, we have also tried to overcome the reliability issue by proposing a segmentation network. Therefore, we know that decisions are focused on the COVID-19 pneumonia only. Also, we have used in this network operational layers so that we have superior learning performance compared to convolutional networks. So in this study, we propose an operation segmentation network that is called OSegNet. OSegNet model can segment COVID-19 pneumonia from chest X-ray images, and it has encoder and decoder parts. So in the encoder part, any deep learning model can be used by transfer learning. Therefore, we have used DenseNet 121 and Inception version 3 state-of-the-art networks for the encoder part. So for the decoder part, we have used operational layers. It has a structure similar to a UNet model. However, we have removed its skipping connections in order to reduce the network complexity. Operational layers are composed of generative neurons that are nonlinear neuron models, and therefore they can have superior learning performance compared to convolutional layers. With operational layers, we can form highly heterogeneous network structures Therefore, we can also significantly reduce the network depth and complexity. So we all know that Taylor a polynomial approximation of a nonlinear function is given as in this equation, and we can represent the nodal operation functions by Maclaurin series where a equals 0. So the input of the nodal operations are the weights that are coming from the Taylor polynomial approximation and the output of the previous layer. So in this figure, you can see the convolutional layers and operational layers differences. Operational layers has the nodal operators and nonlinear neuron models. So each neuron input is calculated by adding the bias of the layer and the nodal operation between the weights of the layer and the output of the previous layer. So each operational layer has kernel size of 3 by 3, and we have added these filter sizes sequentially to our network. The major contribution of this study is the Katakov-19 dataset. It is the largest chest X-ray dataset that includes COVID-19 pneumonia segmentation masks of around 9,000 COVID-19 positive chest X-rays. For the control group, we have used chest X-ray 14 dataset that includes healthy subjects and 14 different lung diseases. We have generated the ground truths by collaborative human machine annotation approach, that is a fast and accurate annotation approach. And also the dataset is publicly shared, and you can also scan the QR code to access the dataset. So we have extend our dataset by using collaborative human machine annotation approach. For this approach, we have annotated data from our previous study. It includes healthy subjects and COVID-19 samples. By using it for the training, we have trained 5 different segmentation networks. For the unannotated data, we try to predict their samples by testing them on these segmentation networks, and we have shown their predictions to medical doctors, and they have selected the most suitable mask for the ground truth. Therefore, we could extend our dataset. So you can see some examples of the chest X-rays and their ground truths in this figure. In data processing part, we have resized all the chest X-rays and then formed our test and trained sets. And on the training set, we have applied data augmentation. From the table, you can see the training set and the test samples after the data processing. In experimental evaluations, we have trained the models over 50 epochs with a learning rate of 10 to minus 4 and a batch size of 32. In figure 3, you can see the segmentation results over the test set of Katakov-19 dataset. We have compared state-of-the-art networks with our proposed OSegNet models. You can see that we have used 2 different encoder types, and for the state-of-the-art, we have UNet++ and DLA models. For the OSegNet, we have set Q to 5 different parameters so that we could investigate its performance as the complexity of the network increases. You can see that for both encoder types, the highest sensitivity is achieved by the OSegNet model when Q is set to 3. And also we can see that the best F2 scores are also obtained by this model. So in this table, there is the COVID-19 detection results. So we detect COVID-19 based on the predictions of the segmentation network. So whenever there is even one pixel predicted as COVID-19 pneumonia by the network, we say that it is COVID-19 in the detection phase. So based on this algorithmic evaluation, we have detect COVID-19 with the proposed networks. So you can see that in this time the detection performance with the high sensitivity is achieved by the Inception version 3 UNet++ model. On the other hand, you can see that with this encoder we have achieved the best precision with OSegNet model Q is equal to 3. In table 5, you can see the confusion matrices of the best performing models, UNet++ and the proposed OSegNet when Q is set to 3 for COVID-19 detection. You can see that UNet++ has higher sensitivity for COVID-19 detection, whereas OSegNet model has higher specificity level. In Table 6, you can see the numbers of parameters of each model with their inference time per sample. You can see that for both encoders, state-of-the-art has the longest inference time per sample compared to our proposed OSegNet models. And we have seen that even with the most complex Q, when Q is set to 5, we have achieved still much less inference time compared to state-of-the-art. So we can prove that the network complexity has reduced. We have also performed severity grading analysis by collaborating with the Qatar University researchers. So we have merged our pneumonia segmentation network with their lung segmentation network to create a demo. So in this demo, you can see that the network predictions of the pneumonia segmentation is merged with the lung segmentation so that we can say the lung infection percentage in total both lungs and also left and right lungs individually. You can access this demo by scanning this QR code. In conclusion, automatic and accurate detection of COVID-19 is a crucial task to prevent further spread of the disease. In this study, we propose OSegNet model and it has achieved the superior performance compared to state-of-the-art deep networks. In this study, we have also overcome the data scarcity issue by proposing the largest dataset, CATACOV-19. We have shown that the most complex OSegNet model, when Q set to 5, has achieved a faster inference time compared to state-of-the-art models, and it supports a reduced network complexity. You can also scan the QR codes to access our dataset or demo. Thank you very much.